Hi everybody! So today we're going to take a look at some examples of windowed calcite from Snellius minerals. These are calcite rhombohedrons where I've cut windows perpendicular to the c-crystallographic axis of our calcite, and this will allow us to observe the optical properties of our calcite along the c-crystallographic axis, which otherwise we wouldn't usually be able to see. Calcite rhombohedrons are used in many of the classic experiments exploring the optics of minerals, and the long and storied history of calcite and optics is probably worth its own nerdy video at some point. But for today, we'll just focus on experiments that you can do with the windowed calcites from Snellius minerals. Here are a couple examples of our windowed calcite, and the different sizes shown here are suitable for different experiments, so we'll actually end up using both of these in our video today. If you'd like to follow along with these experiments yourself, you can find these for sale at the eBay store Snellius Minerals, along with many other very nerdy minerals. We always start off by taking a look at the big picture of what's going on when we study minerals. Our minerals are defined by their chemistry and structure. These in turn determine the crystallography that we'll see at the macro scale, as well as the optical properties of our mineral and how they vary with direction. Our calcite is defined by its chemistry and structure. The chemistry of our calcite is calcium carbonate, CaCO3. And the structure of our calcite consists of planes of trigonal planar carbonate ions with calcium ions in six-fold coordination with the oxygen in those carbonate ions. So that description of the structure of our calcite is a bit rough. However, here is a diagram of the structure of our calcite. In this view, we're looking slightly askew from the plane of the a-axes of our calcite, and this diagram is much nicer than anything that I'd be able to generate in order to sort of show off the structure of calcite. Thank you, Wikimedia Commons, for existing and being a resource filled with all sorts of nerdy goodies. And also, before we move on, I just want you to note that the shape that we're seeing here is indeed a rhombohedron, and we're going to be seeing this shape a lot as we move forward. Let's also mention some calcite background information before we continue on. The hardness of calcite is about 2.5 to 3. This actually varies with direction in our calcite. Calcite can grow in a wide variety of forms. However, all of our calcite crystals will display perfect cleavage. And this perfect cleavage is of the form 1, 0, bar 1, 1, which is a rhombohedron. Calcite isn't very dense, with a density of 2.71 grams per cubic centimeter, and calcite can also display a wide variety of colors given solid solution substitutions of various other metal cations into the structure for calcium, along with the incorporation of other impurities. Calcite is also one of the most common minerals on the surface of the Earth and is very important in a wide variety of industrial applications. Calcite is used for cement manufacture, as an agricultural amendment to adjust the pH of soils, and even as parts of optical instrumentation. Now that we have some background information about our calcite, let's go back out to the big picture, and we can add our calcite structure model into our diagram here. When thinking about the symmetry at the micro scale of our structure diagram, we want to think about the space group symmetry of our calcite, in this case R 3 bar 2 over C. At the macro scale, when looking at a calcite crystal, the symmetry we're going to see is the point group symmetry, in this case 3 bar 2 over M. Let's take a look at a calcite rhombohedron now in order to understand the symmetry and crystallography of our calcite. This rhombohedron is the product of cleaving a larger calcite crystal. We'll rotate our calcite cleavage rhombohedron around a bit so you can get an idea of its shape. Today we're going to go through our calcite symmetry and crystallography rather quickly. However, if you want a deeper dive into what's going on here, you can check out the video Calcite Crystallography. The point group symmetry of our calcite is 3 bar 2 over M. This symbol means that our c-crystallographic axis is going to be a threefold rotoinversion axis, and that our three acrystallographic axes will be twofold rotational axes with perpendicular mirror planes. This view of our calcite rhombohedron is important to us, and right now we're actually looking down the c-crystallographic axis of our calcite. This is our threefold rotoinversion axis. Our A-axes are going to lie in a plane perpendicular to our c-crystallographic axis, and these are twofold rotational symmetry elements with perpendicular mirror planes. We've gotten an idea of the symmetry and crystallography of our calcite rhombohedron, and heading back out to the big picture, I want you to think about the relationship between what's going on at the micro scale with our calcite and what we actually see in a macroscopic cleavage rhombohedron of our calcite. Now we want to add on the optics of our calcite, but in order to do that, we'll first take a look at the optical indicatrix for calcite. This is a three-dimensional representation of the refractive indices of our calcite. If you've seen some of our other videos, we've gone over optical indicatrices before, but here I want to point out what's really special with calcite, and what's really special is the birefringence of our calcite, the difference between refractive index omega and refractive index epsilon. This birefringence is very large for calcite, larger than any of the other minerals we've actually looked at before. When looking along the plane of the A-axes, our birefringence will be 0.172. And this very large birefringence that we see with calcite is caused by the chemistry and structure of calcite. The arrangement of those trigonal planar carbonate anions in our calcite structure means that light is going to travel much more slowly in certain directions through our calcite than in others. Now, our windowed calcite rhombohedrons have windows cut perpendicular to the c-crystallographic axis in order to allow us to view along the c-crystallographic axis of our calcite. When looking along the c-crystallographic axis of our calcite, we'll be seeing the view of our optical indicatrix in the right portion of our diagram here. And this means the light traveling through our calcite in this direction is only going to interact with refractive index omega. And well, in this direction, not really much of anything interesting is going to happen because the light is only interacting with refractive index omega. However, when we take a look through our calcite, viewing from rhombohedral face to rhombohedral face, things will be more interesting. The two views shown in this diagram of our three-dimensional optical indicatrix are currently looking down the plane of the A-axes or down the c-crystallographic axis. The crystal faces of our calcite rhombohedron are actually inclined at 44.6 degrees to the c-crystallographic axis. When we're viewing with our calcite from rhombohedral face to rhombohedral face, we actually want to think about this plane that cuts through our optical indicatrix. In these views, we'll have a section through our optical indicatrix that looks something like this. This is an ellipse that has axes of omega and epsilon prime, where epsilon prime is a refractive index greater than epsilon. In these views of our calcite from rhombohedral face to rhombohedral face, our light is actually going to be split into two beams vibrating in mutually perpendicular directions, and for the very specific circumstances that are occurring within calcite, we'll also get image doubling based on these two rays. There's actually a whole bunch more going on here, and for a more thorough explanation, you should investigate the article Double Trouble Navigating Birefringence. This article is an excellent dive into the properties of calcite and was also inspirational in me making these videos. We've investigated the chemistry and structure of our calcite along with the crystallography of macroscopic calcite crystals, and then we've also talked about the theory behind what we'll see with the optics. Now it's time to actually play around with one of the windowed calcites from Snellius minerals. The larger calcite rhombohedrons with windows are more useful for this experiment where we're looking at an image on a piece of paper in normal everyday light. And when we bring in our calcite rhombohedron looking from rhombohedral face to rhombohedral face, you'll notice that the image in our calcite is doubled. When light travels through our calcite rhombohedron in this direction, it is going to be split into two beams that vibrate in mutually perpendicular directions, one associated with refractive index omega and the other associated with refractive index epsilon prime. When we change our viewing direction through our calcite so that we're looking along the c-crystallographic axis, you can see that we only end up with a single image of our star in this direction. Conveniently, you can also see that the image doubling of our star is still continuing in our rhombohedral faces. With the view through our calcite along the c-crystallographic axis, our light is only interacting with refractive index omega. As such, it isn't being split into two rays vibrating in mutually perpendicular directions, and so we only see a single image of our star. Rotating our calcite rhombohedron with this view shows that not really much of anything is happening in this direction. Now, there are a bunch more experiments that you can do with our view looking through rhombohedral face to rhombohedral face of our calcite, but we've kind of already gone over those in the isotropic versus anisotropic kit video, so I'll send you there if you want to learn more. So our large calcite rhombohedron with windows is great for showing off the anisotropy of our calcite. When looking from rhombohedral face to rhombohedral face of our calcite in normal light, images will be doubled. When looking along the c-crystallographic axis of our calcite rhombohedron through those windows that are perpendicular to that c-crystallographic axis, we'll only see a single image. There are also smaller windowed calcite rhombohedrons available, and these are better for a different experiment using a polariscope. The separation between our doubled images in our larger calcite rhombohedrons is in part dependent upon the thickness of these rhombohedrons. The smaller the calcite rhombohedron, the less distinct each of our doubled images are as they're closer together to one another. Let's take a look at one of our smaller windowed calcite rhombohedrons with a polariscope now. We are currently viewing our smaller calcite rhombohedron with transmitted plane polarized light vibrating in a north-south direction. And we're looking through the windows that have been cut into this rhombohedron so we can see along the c-crystallographic axis. In this direction through our calcite rhombohedron, we should be able to generate a uniaxial optic axis interference figure if we set up our polariscope appropriately. We'll now bring in our upper polarizer so that our view is with crossed polarizers. To generate our optic axis interference figure, we then have to bring in a converging lens. I'm using a hand lens in this example, which is actually of lower power than the glass marble that I usually use to generate these. However, because of the extreme birefringence of calcite, the lower power lens is actually better, or else you're just swamped with isochromes. And it takes a moment to adjust the focus on our microscope and to get everything positioned appropriately, but here you can see a very nice uniaxial optic axis interference figure. Being able to generate this interference figure lets us know we're indeed looking down the c-crystallographic axis, and actually noticing how many isochromes there are and how tightly packed they are let us know that this material we're looking at does indeed have quite extreme birefringence. For comparison, here's an optic axis interference figure for a piece of synthetic corundum. And if you want a much deeper dive into uniaxial optic axis interference figures, you should check out the video Optical Mineralogy Improved Uniaxial Optic Axis Interference Figure. We've gone through the experiments with our calcite rhombohedrons that I wanted to cover for today. Back out to the big picture, our calcite is defined by its chemistry and structure. We examined a structure model for our calcite. And we then examined the crystallography of a macroscopic calcite rhombohedron. This rhombohedron is the product of the cleavage of a larger calcite crystal. We then also discussed the optical indicatrix for our calcite and some of the theory behind what we should see when we were conducting our experiments with our calcite rhombohedrons. It is of particular importance to note that the rather extreme birefringence of our calcite is actually caused by the planes of those trigonal planar carbonate ions in our calcite structure. The extreme birefringence of our calcite, along with the fortunate placement of the cleavage planes in the calcite structure, allows our larger calcite rhombohedron to very clearly display image doubling when looking from rhombohedral face to rhombohedral face in normal everyday light. When looking along the c-crystallographic axis of our calcite rhombohedron through the windows that have been cut into the calcite, we can see that our image is not doubled. This very clearly displays the anisotropy of our calcite, different behaviors in different directions through our crystal. While our tiny windowed calcite rhombohedrons are a bit too small to cleanly display image doubling in normal everyday light, we can actually generate a uniaxial optic axis interference figure with these when viewed with a polariscope with the proper setup. And this lets us know the direction we're looking through our crystal. We are looking down the optic axis of our calcite along with the c-crystallographic axis. So, if you'd like to try out these experiments on your own, the larger and smaller windowed calcite rhombohedrons are available for sale from the eBay store Snellius Minerals, along with many other nerdy mineral specimens. If you have any thoughts, comments, or questions for me, please do feel free to reach out at the email snelliusminerals@gmail.com. Here are the references that I used in the construction of today's video, along with a special shout out to the article Double Trouble Navigating Birefringence. Thanks again for watching this video, and have a great day.